Hello, so we're back for another batch of exam questions. These ones are focusing really on energy, work done, things like that. There'll be a few other bits and bobs creeping in, but mainly that's the gist of it. So let's just crack on with these. Explain what is meant by gravitational potential energy without using an equation. Right, there's a couple of key things you want to put in this. So we want to say that gravitational potential energy is the energy associated with the position of the object. So you want to say position of an object in a gravitational field. So they're the sort of key points that you want here. You want to mention definitely position and the field bit. So we're making it a real potential energy here rather than anything to do with motion. A ball of mass 0 0.2 kilograms, which I haven't put on the picture, 0 0.2 kilograms thrown vertically downwards at a speed of 15 meters per second from a height of 2.8. This is all in it. Rebounds at 12 meters per second. Assume air resistance has negligible effect on the motion of the ball. Calculate the speed of the ball just before it hits the ground. Okay, so this is our conservation of energy SUVAT equation that we've got here. So kinetic energy, final kinetic energy is initial kinetic energy plus the change in gravitational potential energy. That's what this SUVAT equation is. So we're going to have that V squared is, so U squared, 225 plus 2 times 2.8, 5.6 times G. Type all that in. 5.6 times 9.81 plus 225 is that. Square root that. 16.73. We seem to be two sig figs everywhere here, so let's say that is 17 meters per second for two significant figures. Calculate the energy transferred to the ground during the impact. Right, that's going to be a half of 0.2 times v squared, so this 16.73 squared, minus a half of 0.2 of, what's it rebounding at, 12, of 12 squared. That's going to be that energy change. So we got 0.1 multiplied by our difference between these two things. So that was 279.936 minus 144 is that. So that's 13.59. I don't need to put the working out bit there. So that's 13.59, which equals 14 joules, again to two significant figures. Calculate the time of impact of the ball. Oh no, the time of impact with the ball is this, 0.065 seconds. Calculate the magnitude of the average force exerted by the ground on the ball. So F is delta P over delta T, rate of change of momentum. So our change in momentum is going from, what have we got here? So we're going from 16.73, multiplied by 0.1, 0.2, sorry, 0.2 is the mass, minus the 12 times 0.2, and then divide that by our plus, sorry, because we're going in the opposite direction, 0.065. So yeah, we've got a certain amount of, if we're measuring momentum going downwards, our downward momentum before impact is this 16.73 times 0.2. Afterwards, it's minus 12 times 0.2. So we've got that big change there. So 16.73 times 0.2 plus 12 times 0.2 divided by 0.065 gives us 88.4, which is 88 newtons, again to two significant figures. So yeah, the main thing with getting the change in momentum is remembering that momentum is a vector quantity. So we want to take the difference between the momentums, but of course on the way back up it's going to be negative. So we're subtracting a negative, which is why we have a positive coming in there. We want to, how much difference is there by the momentum on the way down and then the momentum on the way up. it's going to be a lot bigger than if they're both moving in the same direction. So that's what's going on there. Right, now we've got a crane, but first of all we've got some definitions to do. So we're starting with a work done by a force. Definition of that, we've had this quite a few times. Work done by a force is the magnitude of the force multiplied by the distance moved in the direction of force. So that's that scrolled down quickly. A crate is pushed along a rough horizontal surface at a constant speed. State what happens to the work done on the crate. So it's the work done against friction, which is going to be going into all of your vibrational losses. So heat, sound are going to be the ones of interest. That's another quick one. Define the watt. 1 watt is 1 joule of work done per second. So some simple starters. Now we've got this crane lifting a mechanical digger. The mass of the digger is 5,200 kilograms. So we've got 5,200 G going down there. It takes 1.5 minutes, so 90 seconds, to lift the digger from X to Y. Calculate the rate of work done to lift the digger. So the power is going to be, well, the work done is the force 5200 G multiplied by the distance. So we're going to have to do some Pythagoras here. 75 squared minus 45 squared and square root all of that. So that's the work that we've done. The time we know is 90 seconds. So let's we got difference of two squares in the Pythagoras. So we're going to have 120 multiplied by 30, which is 3,600. Square root gives us 60. So we got then 60 divided by 90, which is 2/3. So that is going to be 10,400 G over 3. And then we just need to work out what that is. So that is multiplied by 9.81 equals that divided by 3. So 3.4 times 10 to the 4 watts. We seem to be in two significant figures, so that seems fine. Then we've got the total input power to the motors of the crane is 170 kilowatts. Calculate the efficiency. So the efficiency is going to be our 3.4 times 10 to the 4 divided by, that is 1.7 times 10 to the 5. So we've got a 2 and a divided by 10. We've got 0.2, so 20%. So not that efficient, but then again, I don't know how good a crane engine is meant to be when you're lifting things, but 20% doesn't sound that brilliant. But still, that's that question. Right, now we've got fossil fuels will eventually run out. This has led scientists looking for alternative sources of energy. Yep, we know all about this. Tidal stream systems use kinetic energy of seawater to generate electrical energy using tides. Okay, so here's a twin turbine system with seawater turning the blades. Okay, so as water moves around, turns the blades, runs a motor, gets electricity. When operating, we've got 9.7 times 10 to the 5 kilograms of seawater traveling at this speed, passing through each turbine every second, and we get that amount of power. Right, so it's a lot of numbers thrown around, and we can't draw them on a picture, really. Define power. So power is rate of work done. That's a nice start. The input power to each turbine is the kinetic energy of the seawater that flows through each turbine in 1 second. Show that the input power of each turbine is that. Right, the input power. So we want the kinetic energy of seawater that flows through each turbine in 1 second. Right, so we've got that amount of seawater traveling at 3 meters per second passes through each turbine every second. Okay, right, okay, so they've given us a number. So they've already given us the mass. So we just need to do a half multiplied by the 9.7 times 10 to the 5 multiplied by 3 squared. That's all we need to do on this, which is hopefully going to come out with what they've said. So 9.7 times 9 times 0.5 is 43.65, and then we've got a 10 to the 5, so that is 4.365 times 10 to the 6, so that is 4.4 times 10 to the 6 watts. So that's always reassuring that we've got the same number. Calculate the percentage efficiency of each turbine. So that's going to be what comes out divided by what goes in. So the efficiency, the 10 to the 6s are going to cancel. We got 1.2 over 4.4. So 1.2 divided by 4.4 is 2 sevens recurring, so 27%. In 1 second, a cylinder of seawater of mass, that's the same mass, passes through each turbine. That's what we've already told us. Calculate the radius of each turbine. The density of seawater is that. Okay. Right. So how much water have we got going through in a particular amount of time? Right. So if we've got, so density, sometimes people can get a little mixed up with what way round to put all of these things. So we know we need density somewhere. So write out your numbers with the units on. So we've got kilograms per meter cubed for the density. We're going to have the number of kilograms on the other side. So we've got that. We need to end up getting this meter cubed thing put in somewhere. So we need to have, we've got this meters per second here. So we've got a 3 meter length on something, and then we've got these circular turbines. So that's where we're going to get we've got a 3 meter length, and then we've got the area of the turbine. So pi r squared, where we're trying to work out r. So that's going to give us a meter squared. So by the time we've put all of these things in with the units, we can now see we've got kilograms on either side, and now we can just sort things out. So we need to type lots of stuff in. We're going to say that r squared is equal to 9.7 times 10 to the 5 divided by 3 pi times 1030. So what is that giving? 9.7 divided by 3 divided by pi divided by 1030 multiplied by 10 to the 5. So that's going to give us 100, give or take. So by the time we square root it, we're going to end up getting 10. That's the radius of the turbine. Yeah, I find this approach of just working out the units is quite a nice way of doing it. I mean, you can step through it in a different way. I mean, let's try going through this, not just looking at the units and making those balance of exactly what is happening here. So if we're looking at the volume of the water that's going through, you can see it's essentially we're just going to be talking through this equation. So we're saying that we're getting in 1 second, what is the volume that we've got? We've got that 3 meter length. We've got the area swept out by the turbines. So that is our volume. If we multiply the volume by the density, then that is going to give us a mass, because density is mass over volume. So that volume we could put on the other side if we wanted. It doesn't really matter, but we're using that equation and then working things out. It's just a different way of doing it by just doing a unit analysis on it and say, okay, well, let's just put these things, lay these things out. We've got 2 things that have got kilograms in, so we put those one on either side of the equation, because those kilograms have to balance in some way, and then let's just level out those meters. So I mean, I could have put these ones here with the meter and the meter squared dividing on the other side, so we got meters to the -3. It's just a different way of looking at this density equation. Right, so that's all good. Now we're on to the last part here, E. Tidal stream systems require less space than conventional wind turbines that are found in windy regions of the country. Explain why a tidal stream turbine system of identical size to a wind turbine system will produce greater power for the same water or wind speed. Right, well, this is going to be to do with the density of the stuff that's going through it. You think when we worked out the energy that was going in, we did a half mv squared. So we've got this half mv squared is the energy that's going in. If you've got the same V, then, well, we've got the mass has gone up. So the mass is increased because the water is greater than air in terms of water density. Water density is greater than air density. So for the same volume, we've got a greater mass, which means we're going to get a greater kinetic energy. Suggest one further advantage of tidal stream systems over conventional wind farms. Well, one is they're in the sea rather than the land. That's an advantage and a disadvantage. I mean, it's nice that they're out the way, so they don't have them cluttering up the landscape. But it does make them harder to build because you've got to go out into the sea. So we could have that. You're going to have less noise because they're under the water. So that's another one. Yeah, they're the two that spring to mind. There's going to be loads of them, really. You get loads of pros and cons of these sort of things. You got the cons of they're harder to install, they're harder to maintain, that sort of thing. They're harder to connect up to the energy grid compared to a wind farm because it's just so much more accessible on a wind farm. But you do have those advantages that, they're out of the way. So that's an involved question. That's nice.